Way back in the 19th century, chemists were staring at a huge mystery. See, the chemistry of something like a rock seemed to follow one set of rules. But the chemistry of a plant or an animal? Well, that was something else entirely. It was like life had a secret ingredient, some kind of hidden force that made it special. So let's dive in and see how science cracked one of the biggest codes in history. The leading theory at the time was that all living things had this special something called a vital force. And this wasn't just a vague idea, it was actual scientific doctrine. It said that the molecules made by life were fundamentally different and that you could never create them in a lab from non-living stuff. So, was this a real, mystical force, or was science just missing a huge piece of the puzzle? This whole idea had a name: vitalism. You can think of it like a giant wall. On one side, you had inorganic chemistry, rocks, minerals, simple salts, the predictable stuff. And on the other side, the complex, messy, and frankly, kind of magical world of organic chemistry. To the scientists back then, you could analyze a leaf, sure, but you could never, ever build one from scratch. That spark of life, that vital force, was the one ingredient they could never add. But, just like in any good detective story, the official story started to show some serious cracks. New clues started popping up that just didn't fit with this idea of a magical life force. Now, the first big break wasn't some dramatic eureka moment. It was actually something way more basic. They just got better tools. Imagine a detective finally getting a powerful magnifying glass. That's what chemists like Justus von Liebig gave the field. They came up with ways to take an organic compound, burn it, and measure exactly how much carbon, hydrogen, and other stuff was in it. For the very first time, they had a reliable list of ingredients for the molecules of life. And with these new tools, oh man, the evidence started piling up fast. In 1828, a chemist named Wohler accidentally made urea, the organic stuff in urine, in his lab. Total accident, but a huge shock. Still, vitalism hung on. Then, in 1844, Kolbe makes acetic acid, basically vinegar, from totally non-organic materials. That was a major blow. And by 1860, when another chemist, Berthelot, showed you could build organic compounds right from their basic elements, well, that was pretty much the nail in the coffin. The idea of a special vital force was dead. The magic was gone. Now the real work could begin, figuring out the rules. Okay, so vitalism is out. The magic force is gone. Now what? Well, scientists needed a new theory to explain what was really going on. And their first big suspect was something called the radical theory. The idea itself was actually pretty intuitive. It was like organic molecules were built with Legos. The theory was that they were made of these stable, pre-built chunks of atoms called radicals. And these radicals were supposed to be indestructible. They'd go through all sorts of chemical reactions, but the blocks themselves would never ever change. They were, for all intents and purposes, the true elements of organic chemistry. And Liebig and Wohler found what looked like rock-solid proof for this. They took a compound, benzaldehyde, and they just threw everything at it, put it through a whole series of different reactions. And no matter what they did, a core chunk of atoms, what they dubbed the benzyl radical, stayed perfectly intact. It was a huge discovery. It really looked like they'd found their fundamental building block. And I want to be clear, this wasn't some wild fringe idea. Not at all. The radical theory quickly became the way to think about things. For pretty much the entire chemical community, these radicals were the key. The case, it seemed, was finally heading in the right direction. But then, of course, just when everyone thought they had it all figured out, a French chemist, Jean-Baptiste Dumas, discovered something that just blew the whole case wide open. What Dumas found was that the central premise of the radical theory, that these blocks of atoms were unchangeable, was just wrong. He discovered you could actually reach into one of these so-called indestructible radicals, pull an atom out, and swap it for a totally different one. It was like taking a red brick out of a wall, popping a blue one in its place, and finding that the wall was still standing just fine. And oh, this sparked a massive scientific showdown. You had this giant of the field, the great chemist Berzelius, shouting, "No way! That's impossible!" His own massively popular theory said you just can't replace a positive-natured atom, like hydrogen, with a negative-natured one like chlorine. It would break all the rules. But Dumas' experiments were right there. He could just say, well, look, I did it. The proof is in the pudding, and the new compound acts almost exactly like the old one. The evidence was undeniable. So suddenly, everything was chaos, absolute confusion. If the fundamental building blocks weren't fundamental at all, if they weren't unchangeable, then what were the rules of the game? The nice, neat radical theory was in shambles, and for a while, organic chemistry felt like it was back to square one. The real solution, it turns out, wasn't hiding in the big blocks of atoms. To find it, they had to zoom way in, to a single, crucial element that held the blueprint for everything. The whole question had to change. It wasn't what are the building blocks anymore, it was what's the underlying blueprint. Scientists like Franklin, Kekulé, and Couper started asking a brand new question. What's the fundamental rule that tells individual atoms how to connect in the first place? And the breakthrough came from this total shift in perspective. Instead of focusing on the big radicals, a chemist named Edward Franklin started looking at what he called the combining power of single atoms. We call it valency today. He realized that it wasn't about the block, it was about the number of hands each individual atom has to connect with other atoms. And for carbon, the atom that's the backbone of all life as we know it, they found its magic number, the number that unlocks absolutely everything. It's 4. Building on that discovery, two chemists, Kekulé and Couper, laid out two beautifully simple rules that are the foundation of all of organic chemistry. Rule number 1, carbon is quadrivalent. It always has 4 hands, meaning it always makes 4 connections or bonds to other atoms. Always. And rule number 2, and this is the absolute game changer, carbon atoms can use those hands to link directly to other carbon atoms. This is what lets them form these incredibly long, stable chains and complex rings. And that was the secret blueprint. Those 2 simple rules explained everything. They could explain the simple chains in fats and the incredibly complicated rings of molecules like benzene. The unbelievable diversity of life's chemistry wasn't because of a vital force or indestructible Legos. It was all down to the simple, elegant, predictable bonding rules of a single atom, carbon. So, when we step back and look at the whole story, it's not just a series of lucky guesses. You can actually see a clear, logical, step-by-step process of scientific discovery at work. The path is always pretty much the same, right? You start by getting better tools. Those tools let you make new discoveries. Then you propose a theory, your best guess, to explain what you've seen. But then, inevitably, you find new evidence that just doesn't fit, that breaks your theory. So what do? You throw out the old theory and build a new, better one that can explain all the evidence. That's how science moves forward, by constantly finding the holes in its own best ideas. And this, for me, is the most important takeaway, that radical theory wasn't wrong in a foolish way. It was a brilliant, perfectly logical explanation for all the evidence they had at the time. It was a necessary, productive, and absolutely essential step on the path to a deeper truth. These so-called failed theories aren't dead ends at all. They're the stepping stones you have to walk on to get to the other side. Which leaves us with a really fascinating thought. If this whole story shows that today's solid, bedrock scientific facts are built on the foundations of yesterday's wrong ideas, well, it really makes you wonder, doesn't it? Which of our own modern certainties, the things we know are true today, are really just the next stepping stone on a path to a deeper truth we can't even begin to imagine yet?